Okay, so welcome again to a panel discussion session of the afternoon. Today, we are going to talk about quadratic gravity, effective field theory, and modified gravity, use and limitations. And today, the panel is composed by Robert Brandenberger of McGill University, Astrid Eichhorn of CP3 Origins, Southern Denmark University, Giulia Gubitosi of Napoli Federico II University, Lavinia Heisenberg, Heidelberg University, and fellow Stelle of Imperial College. So, effective field theories. Effective field theories are tools in field theory to describe situations where we are interested in, generally speaking, in energies much below some big energy scale that is referred to as the cutoff. So we have an advantage. We have this large hierarchy of scale, and in effective field theory, one uses this hierarchy of scale to perform an expansion in energy divided by this cutoff. Okay, so but this is a workshop on quantum gravity. So I'm mainly interested in effective field theory for quantum gravity. And although we are also interested, of course, in coupling gravity to matter. So in order to be consistent, we also have to construct an effective field theory that includes, at the very least, the standard model fields and perhaps some other fields needed to account for the phenomenological problems of the standard model, such as dark matter, neutrino oscillation, and baryon asymmetry. So the higher scale in the case of gravity is essentially the energy scale at which you perform experiments, and at most the Planck scale. I'm going to say later on that maybe the scale, the cutoff scale, can be a little bit smaller in some cases, but at most should be the Planck scale. So, do I have a pointer? Just use this. Okay. Besides the cosmological constant and the Einstein-Hilbert term, then we have to add in the gravitational part of the action, the Lagrangian, all possible terms that are compatible with general covariance. So going at the quadratic level in the curvature, we have what I've introduced in my talk, the quadratic gravity part. But then we also have to include terms cubic in the curvature, and so on and so forth, quartic in the curvature, etc. So we have to include all the perturbatively renormalizable and also non-renormalizable terms in the gravity and matter sector too. So in these dots, I mean that you should also include the matter fields, but the way it appears is a little bit model dependent, so I'm not showing you anything. You should understand that they are there. Okay. Up to quadratic in curvature terms, then this effective Lagrangian reproduces quadratic gravity, but there are two important differences. One, basically, I've already said that it also includes higher curvature invariance, terms higher in the expansion in energy over the cutoff scale. But most importantly, I would say, the extra terms, in addition to the Einstein-Hilbert, the cosmological constant, first two in this line here, and the renormalizable matter terms are treated perturbatively. So we have, in the case of the effective Lagrangian for gravity, we have to treat this C2, C2 prime, C3, C3 prime, etc. All these CI coefficients as small perturbations. If they are not, we are outside the range of validity of the effective field theory. And this treatment, this perturbative treatment, also allows us to say that these infinite terms do not lead to extra degrees of freedom, besides the massless spin-2 graviton and the matter degrees of freedom at a renormalizable level, the degrees of freedom of the standard model or some other fields that are required for the phenomenological reasons I said before. Because if you treat these coefficients perturbatively, they do not appear in the pose of the propagator, so this is a crucial feature of the effective field theory. So we have discussed several modifications of gravity. The effective field theory of gravity captures all energy modifications, of course, in the regime of validity of the effective field theory that I've stated before. Below, so a maximum energy scale, whatever is cutoff, at which it breaks down. And this scale is basically the minimum between the Planck scale and if these coefficients Ci, maybe there's one that is very large, then the cutoff goes down to m Planck divided by the maximum value of this coefficients. So you can have scenarios where you have a lower cutoff. For example, some years ago, as I was mentioned this morning, it was proposed this model of large extra dimensions where the scale of quantum gravity is lowered down to basically energies that are accessible at colliders, and this is done by introducing indeed large extra dimensions, so large that this can happen. And in this case, the cutoff scale of the effective field theory of gravity becomes very low compared to the Planck four-dimensional Planck scale, because the higher dimensional Planck scale is much lower. So there are cases in which the cutoff indeed is much lower than the four-dimensional Planck scale.
You're referring to DGP type things. No?
The ADD,
ADD
large
ADD
extra dimension scenario.
Okay.
Yeah. For example, there may be some other examples. Okay, good. So I would be very direct with my questions because I've been asked to be not so long in my presentation. So I would say that the most interesting question, which is the master question in this discussion, is the first one. What are the physical situations where you can probe the limitations of the effective field theory of gravity? I think this is very important because this is the place where you can try to have information on a UV complete theory of quantum gravity. Because where the effective field theory breaks down means that there must be some input from the UV complete theory. And then there are all these following questions. Can we consistently describe black holes in the effective field theory of gravity, given that GR predicts a singularity? This is a sort of tricky question because, of course, when you are at the singularity, the curvature are infinite. So in particular, they're much bigger than the Planck scale. So you're clearly outside the regime of validity of the effective field theory. But if you are far away from the singularity, this is not the case. So it is not obvious whether or not you can use effective field theory of gravity. What is the precise limitation there? If you're not able to use the effective field theory of gravity, then a question that maybe this is for Kelly, what is the endpoint of gravitational collapse in quadratic gravity, in your opinion? Or maybe somebody else who wants to answer this question. If instead the answer is yes, how can the black hole singularity be consistent with the finite cutoff of the effective field theory? And then I also added this question related to black holes. Does the effective field theory of gravity break down close to an event horizon? This is also, to me, a kind of tricky question because from one point of view, the curvature is small there. So one would say, okay, the curvature is small, then you can use effective field theory of gravity. But there is an information puzzle that suggests that fundamental theory may show up because of the presence of an event horizon. So I think this is also a not obvious question to ask. And then the last question that came to my mind, but also put some thoughts here, in the sense that maybe many other questions to ask, is can we understand the mechanisms that select the initial conditions for inflation in the effective field theory of gravity? This is, let's say, can be understood in two ways, either the initial condition for the inflaton, so why the initial condition is for the, let's say, the background part of inflation is homogeneous and isotropic, or what selects the initial condition for the perturbations. So we already know Robert's opinion about this latter aspect of the question, but I think it's important to discuss more about this because maybe it's a little bit controversial. And then, of course, feel free to ask many other questions. I'm sure you have. So I would say let's start the discussion. And I would proceed by alphabetic order in the surname. So I would ask Robert to start his discussion first.
Okay, so like in the first panel I was on, I'm going to take your questions and I'm going to try to address it a little bit. And I'll invert the order for the questions. I guess you're not surprised which question I'm going to address first. So these are the questions which you just saw. And I'm going to talk about the question about the initial conditions for inflation. So I would repeat my claim that inflation cannot be described in an effective field theory approach. And based on discussions I've had here, I think I do want to add a couple of space-time diagrams on the board, just to make sure that we all understand this criticism of Transplanckian censorship. So I will draw three space-time diagrams, one corresponding to inflation, one corresponding to a bouncing cosmology, where this is a bounce point. Here, this is the end of inflation. This is the beginning of inflation. This is the Big Bang and inflationary cosmology. And here, I will also have the emergent cosmology, where there's the emergence of time and then the space. Okay. Good. So we have to draw the Hubble radius. Hubble radius. Hubble radius. And then we have to draw the length scale of ignorance, the Planck length. So the basic claim is that this is a zone of ignorance. It's a zone of ignorance in all models. And this is simply a zone of ignorance which says that the physical K that we are dealing with at any given time always has to be smaller than in Planck. Okay, now there's a second criterion which indicates the breakdown of an effective field theory, and this is high curvature. Okay, so now in the inflationary setting, there's high curvature zone of ignorance here. So for quadratic gravity, it is in this zone, in this region, where we will have to include all higher order curvature corrections in the action. So I want to emphasize that these are completely different zones of ignorance. Now, in the bouncing cosmology, you have this zone of ignorance at the bounce point. You need physics beyond effective field theory to give us the bounce. And in a certain sense, in the emergent cosmology, the whole thing is a zone of ignorance. Because, so, okay. So now the statement is that if you go from Einstein gravity to quadratic gravity, you are not changing anything in terms of the transplanting center of conjunction. But now, if you want to, if you want to get inflation, you will need a non-perturbative setup. And if you indeed have a non-perturbative setup which gives us inflation, then this non-perturbative setup, this quantum gravity, would provide the initial conditions for the fluctuations. However, again, this is important. Alternatives to inflation exist, and I think they're more likely. Okay, good. This already illustrated. Good. Actually, I don't want to monopolize too much, and so I will not say anything else. I have a couple of other things prepared, but this is not so important.
Maybe you can continue.
No, I don't want to continue because it may be more So I don't. The other points were not so relevant as this.
Slides. And well, Astrid is on. Okay, so Astrid, please. Do you have slides or?
No, I don't have any slides. Hi, can you hear me?
Yes.
Okay, very well. So I just have a few remarks that I would like to make. The first is a very sort of general word of caution about how we think about effective field theories and their breakdowns, because in many arguments that are being made about the regime of validity of an EFT or the structure of an EFT, what is generically assumed is that there is a single scale of new physics and that all of the coefficients that we have in front of the higher order terms are all, well, generically of order 1 or of the same order. And I think that is a very specific assumption about EFTs. It says that is not just an EFT we're looking at, but an EFT that is sort of natural. It can very easily happen that a UV completion generates an EFT in which some of those coefficients are even many, many orders of magnitude larger or smaller than others. You can easily construct examples if you just have slightly non-trivial structures in the renormalization group flow, for instance. And so this is just a general word of caution that whenever we talk about EFTs and their range of validity and when they will break down and so on, that we don't fall into this trap of just talking about the natural EFTs, but that we also think of examples like Starobinsky inflation would be a very simple example. We would generically expect that the cutoff scale of the whole gravitational EFT is the Planck scale, but Starobinsky inflation is nevertheless used in cosmology quite a lot. And in order for it to make sense, it's the curvature squared term that has to have a significantly larger coefficient, but not all the others, right? It would be the curvature squared term that dominates at scales of inflation without all of the other higher order curvature terms at the same time becoming important, because if they would become important at the same time, then that description of inflation would break down. So this is sort of one example that practitioners in cosmology use a lot, that is an unnatural EFT. And so this is just sort of a general thing that I wanted to say when we talk about the breakdown of EFTs and the gravitational EFT. We have to keep an open mind that we should also think about situations where some of the coefficients may differ by many, many orders of magnitude. And so I think that this is one of the things where it becomes interesting to think about the physical situations in which we can probe the EFT of gravity a bit more. So if we keep an open mind as to the size of the coefficients and look at EFTs that are unnatural and similar to Starobinsky inflation in that selected higher order curvature terms come with very large coefficients, but not all of them, then we can easily come up with astrophysical situations even where some of these higher order curvature terms become important. So one example that you can construct would be in a scalar tensor theory of gravity, where if you have an appropriate coupling between the scalar and Gauss-Bonnet invariance, you can get scalarization for black holes, and astrophysical black holes can completely change their properties in a detectable way. And that happens if the mass scale that is associated to that coupling is just sort of unnatural and not given by the Planck scale, but by a very different scale. And so those types of unnatural EFTs we can probe with experiments nowadays. And of course, they already can give us a lot of information about the underlying UV completion, because if we find indications for some of the terms in the EFT being much larger than others, then that tells us that there has to be a UV completion that is able to generate such non-trivial structures. And so that was all that I wanted to say as the initial remarks, and I'm looking forward to the actual discussion.
Okay, thank you very much. Then now I'll ask Giulia to say her opinions and other statements, if she wants, about this topic.
Yeah, so I will keep with these words of caution that have been started by Robert and Astrid, and put on some more. So I was a bit concerned when you said you brought the effective field theory action to gravity, and you said this encodes all the modifications we have. Of course, that comes with assumptions. For example, you are requiring locality, local Lorentz invariance, and so on and so forth. So there is a bit of a risk of considering an effective field theory as the most general modification to the theory we have that goes in the direction of the fundamental theory. And I think this links also to what Astrid was saying now, but you might be missing on features that the fundamental theory has that you want to have also in this intermediate regime where you describe gravity, the effective field theory, than that you do not have in the general relativity action. And this leads to the question of what is the relation between this effective field theory of gravity and quantum gravity. So this could be seen as a modification of classical in the meaning of non-quantum general relativity. It is not clear at all that that's what you would get if you started from a full-fledged quantum gravity theory and went down to the scales. For example, think about Orava-Lipschitz gravity. That is another model of gravity that has some normalization properties that you would not naturally encode when you write an effective theory of gravity of that sort. So again, on this, it is okay. It can have useful features to do phenomenology, so to give you a framework to search for departures from general relativity. But at the same time, it can be too constraining already, so you might miss some things. Think about, I don't know, when general relativity was developed, you had Newtonian gravity, and then what could you have done? Maybe do some post-Newtonian expansion, but you wouldn't do it without knowing already the full GR. So it is really hard to guess what are the modifications to the theory you have without having any experimental hint. So at the time of general relativity, what happened was that we had observations that guided us towards the theory. Here we don't. Or even worse, think about the transition from classical physics to quantum mechanics. It's a complete change of paradigm. It would have never been done without the help of observations. And if you wanted to write first order in some scale modifications to classical physics, because quantum mechanics would not have been possible. So it's more words of caution to add. I think they go a bit in the direction of what Astrid is saying, that if you start from a fundamental theory, you may have that terms that you wouldn't expect to be relevant or more relevant than others just because of the coefficients, or you may have to consider completely new kind of formalism.
Okay, so I would then turn to Lavinia. Lavinia, can you hear me?
Yes, I can hear you. Hi, everyone.
Hello.
I hope you can hear me well.
Yes.
Yes, thank you very much that I was able to participate in this format. So very interesting thoughts so far. I completely agree with the majority of what has been said. I guess one immediate limitation that comes in mind when you see this standard effective field theory, I think Astrid called them natural effective field theories, is exactly what you said, that there is one scale associated to that. And if you try to get new physics from this specific operators, and whenever this operator becomes large, in order for you to get appreciable new effects, then you run into the problem that there are also a bunch of other unphysical degrees of freedom or ghost degrees of freedom or whatever that you actually also that you are going to introduce, and your effective field theory basically breaks down. But I guess so you can use those standard effective field theories as long as you are willing to stay very close to general relativity, in which you are aware that your effects will be super duper tiny, very small. But the type of effective field theories that we are interested in cosmology are this unnatural, that Astrid called them unnatural. I would call them non-standard effective field theories, in the sense there were, all these operators rearranged themselves in a way such that they become very, very strong and even dominant in the low energy regime, and then you can get very high new effects, which is very far away from GR, and nevertheless not run out of the validity of the effective field theory. So in this sense, like in the diagrams that Robert was drawing there, if you have an effective field theory, like the ones that we use in cosmology due to these additional degrees of freedom, like in the Galilean theories or generalized Broca, because you have this additional vector field whatsoever, the EFT is such that you have different scales of where these operators kick in, and then if you can manage, for example, to get inflation or just bouncing solutions within the regime of effective field theory, where these operators become dominant or important, yeah, you can get this new physics without running into this problem of ignorance regime, or that you find in yourself dealing with infinities, or that your EFT breaks down. Maybe another second limitation of effective field theories is that, as soon as you have these general descriptions in terms of like the symmetry breaking pattern that you have considered, then it's very hard to really say this observable relates to this very particular physical effect. And in order maybe to get hint for this, it's then better to consider concrete covariant theories where you exactly know where this new physics for this observable came from. So maybe one would need to use this non-standard effective field theories hand in hand with very concrete covariant Lagrangians, where you can then make this mapping or analogy so that you know, can I even realize that in a very concrete theory such that certain observables behave in a certain way. I think that's all what I wanted to say for now.
Okay, thank you very much, Lavinia. And then the last one is Kelly, please.
Okay, well, happy to be here. I have to say on this general topic, I don't have much in the way of any conclusions, but I have lots and lots of questions. My first question that's stimulated by this whole topic that you raised is, I'm not quite sure what the sort of standard approach to renormalization or developing the effective field theory actually means. I think I sort of follow some of the complaints of Gerard de Tooft on this, who of course knows how to renormalize the standard model. He raised his finger at conference a long time ago about that. I.e., and for example, with the mass renormalization, when you renormalize a mass, you have a finite part that's left over. You don't just subtract the infinity and say that's it. You normalize the mass to zero. You don't do that. You have a finite part that remains, which in fact is going to change with renormalization to a scale. And that gets into the propagator. So you look at the physical consequences. That mass is definitely part of the propagator. And I don't see any real reason why you shouldn't do the same thing in gravity. If you start out just with Einstein's theory, you say, oops, one loop, you get curvature squared infinities. You would like to get rid of them, but you can't get rid of them to zero. So you get rid of them with a residuum that's going to depend upon your normalization of scale. And the natural procedure, if you are quantizing about flat space, and I have to underline that to see assumptions, the natural thing is to go back and do what you would do with the mass, which is you reincorporate them into the propagator and then go further with that, which essentially means renormalize. You've discovered that you've made the theory renormalizable, and then you work with that. You get the higher order coefficient, higher order terms anyway, but you get them with finite coefficients, having solved to infinity. I suppose another point of view is maybe you say you don't know if you're renormalizing around flat space. You sort of throw your hands in the air about all sorts of backgrounds, and you try to renormalize around some sort of generic condition. I have to admit, and this starts to be where I have questions. I'm not quite sure I really understand what functional renormalization calculations are. I'm sure some of the people in the audience could instruct me on that more. There's a basic question in my mind about the interrelation about these two attitudes. One is definitely going to produce all the infinite number of R cubed and higher coefficients, apparently now with infinite coefficients. But so that's what I wanted to say, that the sort of naive approach is, in fact, once you encounter an infinity, you have to go back and remember that it has a finite, there's going to always be a finite residuum, which you have to take into account in the Feynman rules therever after, right? And if that changes the power counting, well, you just react to it. I think my attitude towards all of this is at first address the renormalization problem, maybe go out for dinner, and then worry about whatever the degrees of freedom look like afterwards. And see if you can make sense of this theory. So issues about stability of the famous ghosts and so forth, McDonoghue's point of view can come into play at that point, which you have to look at the consequences, all the finite consequences of Feynman diagrams as well. So that's, like I say, this is where the borderline between, this is where my questions start. And so basically all I have are some families of questions about this. Another aspect of it, however, is once you realize that these other terms are there in general, there are going to be all sorts of other solutions, such as interesting other solutions of black hole structure and so forth. And then the question is, what does that do for the overall physical impact of the theory? There's a toy model of all of this, which you could work with, and I've never seen it really done in a complete professional way. It's a little bit dumb. You just take ordinary Yang-Mills theory or even electrodynamics with heavy fermions and integrate them. Say the fermions are the electrons are very heavy, and integrate them out, right? And then this generates a mess for the vector fields. Which looks very much like this sort of effective field theory. And indeed, you also have the same problems. You have extra apparent modes that come in because of what you've done. But actually, you shouldn't really worry about it because it's actually just QED. So the defects that come up basically solve themselves once you realize that you reach there's going to be some energy scale at which all hell is going to break loose, because you've integrated out these masses, and that's the limit of the effective field theory, where you're supposed to remember, actually, there were fermions in the story, and that's restatement. My feeling on all of that is if you're going to do this, actually, we're in a kind of, there's an adjective meso that's being bandied around here. I'm happy to deal with all of this as a kind of an asymptotic safety type meso-effective field theory, waiting upon a final actual underlying theory, my own taste would be something extremely. But it's the main interesting questions, I guess, for this sort of discussion is what can you make use of this meso theory anyway in the meantime, in particular without getting terribly excited about the ghost, and perhaps because it develops an imaginary part and it's just a resonance for most of the energy ranges that you're talking about. And then I have a whole bunch of questions too. Whether you can find regimes, at least, in which you can do things like, I haven't mentioned inflation because that's really the topic that you've raised. I guess you have to convince me. This picture is interesting here when you crossed out a bottom part and saying that, of course, is where the higher derivative terms start to get involved in normalization, but you say they don't help at all. Okay, I hear that. I'd like to understand that better. And then Astrid raised another important point. Like I say, all I have are really questions, no solutions. But in particular with Starobinsky inflation, it's always seemed, in order to make it work, you have to have the curvature, the R squared term, have some humongous value in order to make the potential that you like. On the other hand, in renormalization, it mixes gregariously with the other curvature squared term. So to treat the R squared as having a big coefficient and the other one, I wish you never heard about it, i.e. would like to have a value of 0, strikes me as extremely asymmetric and not very well justified. So these questions are inseparable. And that's about all I really have to say. I have many more questions which come up every time somebody else makes a point. I think about 5 things to ask questions about.
Okay. Okay, thank you very much, Kelly. Can I switch to my slides?
We would keep to
Because otherwise we don't see the two of them.
Okay, so just to maybe clarify something said. Yes, as I showed in my slides, some of these coefficients could be of different order, and when they are of different order, the cutoff is somehow different. So as I showed in my slides, the cutoff does not have to be necessarily the Planck scale, but it can be lower.
Yeah.
For example, if you have Starobinsky inflation and you demand the theory to have just a spin-2 massless graviton, it means that you cannot describe the Starobinsky inflation in this effective field theory, and the cutoff is no longer the Planck scale, but is the Planck scale divided, roughly speaking, by the coefficient of the R squared term, which makes it lower, more or less, of order 10 to the 13 GeV. That means Starobinsky inflation cannot be included in that specific effective theory you showed, but this doesn't mean that you cannot construct another effective theory, which in addition to the massless graviton also has the scalar of Starobinsky. And that other effective theory will not be constructed in a way that the low energy spectrum only has massless spin-2 graviton, but also has this additional scalar degree of freedom. Then on top of that, all the other higher curvature terms should be treated perturbatively in this new effective theory. I guess that whatever modification you do, if you go at low enough energy, you have to reduce to standard gravity because there are constraints. So this means just that the effective theory will have a very low cutoff, nothing else. So I have the feeling that everything, once you require the observations to be described, will be described by an effective theory. It's just that the cutoff in some cases can be very low. This is the first clarification I wanted to add. And yes, this is a very good point, Kelly, about renormalization. So when you do renormalization, there will be infinities. And these infinities can be reabsorbed in these coefficients. So if you, for example, start computing loops in Einstein gravity with just the Einstein-Hilbert term at sufficiently high loop level, all this coefficient will be generated, will be infinite, and so you have to put it in the Baire Lagrangian in order to reabsorb all these infinities. And so you
could
have
just
an
inject a
infinite
word
number
about terminology. When people talk about non-renormalizable theories, your task in any case is to renormalize them. You have to still renormalize them. You got to do something about the infinity if you want to make any sense of it.
Yeah.
So there may be an infinite number of them, but you do, as Weinberg has emphasized, you do have to subtract the infinities, and that is renormalization.
Yeah.
So non-renormalizable is a string in units. It's,
in a sense, renormalizable theories are also renormalizable as long as you put all the possible infinite terms. The problem is that when the energy go to the cutoff scale, all these infinite parameters become important, and the theory unfortunately becomes unpredictable. Unless you have maybe some asymptotic safety regime where you have some critical surface, and then if you're very lucky, then maybe this problem can be avoided. Then at this point, I would ask, yes.
So you ask me a question. Let me try to answer.
Would like to hear.
Adding one to the graphs actually. So what I actually didn't plot in this graph is the wavelength of cosmological perturbation. We measure cosmological perturbation. So what happens in inflation, we trace back what we see today. And what happens in inflation is this. What happens in bouncing cosmology is something like this. And in emergent cosmology, something like this. So, and you see that however you modify the action that gives you the background will not change this problem. And that's what I wanted to add in this concept.
Just affecting the bottom of your well rather than
right. So like
I gather that was what you were saying. What if you have a better control of the hatched area to the left, though, that you actually know what you're doing? It's called string theory. Well, that's maybe your whole point, that you think you do.
Yep. So the question is which of these, so whoever has a quantum gravity proposal, then which of these scenarios will emerge? Or will something else emerge? It might be, these are just three possibilities. So Giulia, you know that João Marguija would have other suggestions. So again, I want to emphasize that here, I'm talking about three cosmological scenarios, which I happen to have worked on, but this is not an exclusive list.
But in your talk, didn't you give a little regime where you could use an effective field theory? You just didn't like the numbers that came out.
You mean coordination?
Yeah.
Yeah. So you see, my criterion was I want scales which are classical, not to emerge from this region.
Right.
And so if you have a very low scale inflation that the Hubble radius goes way this way, then you don't. This is how you open up this little window.
Mm-hmm.
But the cost of that is that you lose the computation of the amplitude.
Alberto is raising all the issue about scales and playing with different scales. Is that so? There are various knobs we can turn here.
See, I think so I noticed that in this discussion, there was often a confusion between this region of ignorance and this region of ignorance. Mm-hmm. So, and I think, again, the discussion about tuning the knobs, and again, what Astrid and Lavinia were addressing is basically what are the terms that have to be included here, mm-hmm. and here, and here. But this is separate from this one. I don't know.
Okay.
So I think it's Lavinia though.
Oh yeah.
Raise
Yeah, I just was wondering, like, the way how you wanted to renormalize, and you said you want to observe the infinities in the mass term. In this way, you would explicitly break diffeomorphisms, and your Feynman rules should know about the fact that your original theory was GR, which was completely diffeomorphism invariant, and they shouldn't be able to break explicitly the diffeomorphisms so that you could have actually a mass term. And if you allowed from the very beginning for a mass term, because you're explicitly then breaking the diffeomorphism invariance, then actually all your loop calculations, both from gravity and from matter fields, will also generate a bunch of new diffeomorphism breaking operators. So I guess in gravity, we are kind of like forced to accept the fact that we have in the standard language non-normalizable theory, and then one either has to give up on this technique of renormalizability like we are used to with our standard theories, and if one assumes that actually we have to give up on that, and this is where the effective field theory or the use of effective field theory enters, right? That we don't even attempt, or we are not even interested in renormalizing the theory. We're just saying whatever the UV theory is, for my low energy physics, it will not have any effect than that what my effective field theory is already describing. That's basically like a change of philosophy.
I think there's a failure of handshaking in terms of what I said. When I was referring to mass terms, I'm referring to another renormalization problem, which is just a standard particle physics renormalization, say, the standard model, where there really are mass terms. And that's a separate issue. Once you are renormalizing the mass term, it's going to have a finite part, but that finite part better be in the propagator, and then you go forward with there.
So you were not referring to the mass of the gravity?
No, I wasn't. No, that's the handshake.
He was not referring to the mass of the gravity.
If you're renormalizing in gravity, I only want to have a coordinate invariant counterterm, please. I mean, that's, yeah, otherwise it's a mess. So I personally like the background field method, which ensures that that's what you're going to get.
Mm-hmm.
So no, I would not renormalize it as a mass term separate of anything else. That would be horrible.
Okay, I misunderstood you.
Okay, thank you. Just another remark I wanted to make is that what I define as, I call the quadratic gravity, is not an effective theory, in the sense that, as I discussed in my slides, these coefficients C2 and C2 prime are not treated perturbatively by definition of quadratic gravity. While in this effective theory I introduced in the slides, all these coefficients, the C2, C2 prime, C3, C3 prime, all the CI are treated perturbatively by definition, by construction of effective theory. Okay, this is a remark I wanted to make, and then I would ask the audience if they have questions. Yes,
I have some remarks. One was concerning the term model that he was referring to when you integrate out the Fermi loops. So, for example, you say we can test this kind of term model. For example, what occurred to my mind, I don't know if I understood you correctly. You know that you can derive the Schwinger-Lagrangian by integrating fermion loops, and then if at the lowest order, that is the Euler-Heisenberg Lagrangian, which is basically the standard Lagrangian for nonlinear electrodynamics. There is a setting where this Lagrangian is used, which is in describing basically the propagation of photons between parallel plates of a Casimir effect. And there, even at low energy, low energy photons, you have something weird going on, because you find out that the photons going between the two parallel plates are going faster than the photon going parallel to the parallel plates. Actually, they are going faster than light. It seems very odd, because you have apparently the photon parallel. It is very obvious what is going on. No? You have that the vacuum has a preferred direction, and there is a vacuum polarization, which basically opens the light cone orthogonally to the plate. And it's just an example where you don't need to arrive to the breakdown to the theory to start to see that the theory probably is not fundamental. Why? Because if the theory is fundamental, imagine you don't know where you derive this Lagrange. And I ask you, is this fundamental? The problem is that if it is fundamental, you start to be worried because it will be applicable at arbitrary high energy of the photon. However, that would create a causal paradox, because if you insist, if you don't realize that you are in a world where there's vacuum, the Lagrange is Lorentz invariant. You imagine you don't know where you are between the parallel planes. You're doing your observation there. Then, in principle, you can build a time machine faster than light photons in that direction, plus Lorentz invariance is all you need to build a time machine to close a time loop. It's a well-known problem. And that what is telling you that simply the resolution is very simple. What really is the speed of signals is the velocity, is the phase velocity in the limit of infinite frequency. In that limit, Heisenberg Lagrangian doesn't work anymore because in the soft photon limit we derive it. We cannot neglect the thermal loop. So, but people, for example, is trying to build time machine with this kind of effect. I proposed that you can put together parallel plates with a small hole to close time like plates. So I'm just saying that is an example where you have a theory which is Lorentz invariant, perfectly fine, is nonlinear electrodynamics derived in this way, is an effective theory. And you can see that there must be something breaking down in the high energy regime, because otherwise you incur in the possibility to build up a causal paradoxes. So there are sometimes ways to see the theory need a UV completion, even without observing, the breakdown cascade, because the causal paradox can be generated. It is even better. The lowest the photon, the better it works, the theory, because it's taken in the limit of low energy. And another small comment I have concerning the possibility to avoid the Big Bang singularity is that you can categorize them. If you ask, imagine that I want to untrap, you go backward in time. What is happening is that the trapped region, all the universe, any point in the universe becomes trapped. And what is happening is that in order to avoid the Big Bang, you have to untrap any point of the universe, because all the points of the universe are equivalent. So you can categorize the way to avoid the Big Bang. And basically, you have three possibilities if you do that in a systematic way. One is the bounce. One is the emergent universe that Robert was also introducing, with or without oscillation of it. Another one is a universe which go back in time, arrive to a universe, and then instead of being emergent with a constant scale factor, the scale factor tends to go to zero, but at infinity in the past. So these are all the possibilities. The only way to not have this is that really you don't have a regime where you can introduce any metrics to describe. Normally, when you do a bounce, conceptually, you see what Robert wrote. You say there is a region of ignorance in the bounce, horizontal one. Normally, it's not that we have a metric that describes a minimum scale factor and then expands again. But what we are saying is that that probably metric description doesn't hold. But you can analytically continue through that. You can imagine that your scale factor arrives to a minimum and then expand again. And the same you can do in the other situation I discussed. In principle, you can categorize in a quantum gravity way the ways to undo the singularity of the group. And there aren't many. So basically what Robert has covered, I think, is quite exhaustive. In my point of view, there isn't much else that one can do if we don't give up analyticity of the net. I mean, you have to do something more radical. That normally people doesn't find when they do this model of quantum gravity. They found the simple bounce, the emergent universe, but they don't find anything more radical.
See, what I was thinking of a different scenario was the varying speed of light scenario. Now, how does that fit into your practice?
Okay, I worked on varying speed of light. So let me try. First of all, varying speed of light, we have to agree the way you do it. Because if you take a constant of nature and you promote it to be dependent on time, that's bad. You create an external field that doesn't breaks general covariance. You don't have identities. That's bad. So you needed to give a dynamic to this. You promote the speed of light to a field, you give a dynamic to this field. I think that there, at the end of the day, you still have a problem of solving. The problem is that you want to drive also the curvature to have special sections. And that one is not easy to do with just the varying speed of light. With a varying speed of light, you can generate a perturbation because it's like time varying refractive index, you excite perturbation, that's true. And if you do it with the right scaling in time, you get the Harrison-Dodge-like spectrum. Fine, that you can do. You can do the horizon problem. It's very difficult to do the curvature problem. Well, I don't think that the varying speed of light proposal is complete from that point of view. And once you try to do it complete, you need basically to do something which is too similar to the mechanism of inflation to be really completely original.
Let me try to put words into Joel's mouth. He might say that he's giving up on one of the principles that you were using, this general covariance.
Yeah, but then I would say that to me that is more fun. I mean, it's what I define to be a gravity theory. But then, and there is a paper also by Donahue that was trying to build a breakdown of general covariance and to try to constrain it. I mean, there are severe constraints. Now I cannot remember on the top of my mind. I remember this paper by Donahue. So, but you see, what is gravity? At the end of the day, what is a theory of gravity? If you give up, I'm happy to give up, to give up Lorentz invariance, you introduce another dynamical field, another, and then you have a metric, and this is just, but it's still a covariant theory. If you give up covariance, I feel a bit, I don't know, but then at that point, I go for non-perturbative gravity.
I think I agree with that. I just want to be conservative. If anyone, because if anyone in the audience has another scenario, you see, I don't want to feel them offended.
I just wanted to add, I rather like your Euler-Heisenberg analogy, which is a signal, a litmus signal that this is an effective theory. And and of course, if you built it as an effective theory, it's an effective theory because you know what you did, right? So you integrated out the electrons with a certain mass, and you know what's going to happen eventually when you get to the right energies, you're going to start having pair creation. And if you've left that out, then the theory breaks down. But what's interesting about your example is there can be problems also at lower energies. Now, I come back to gravity, which to me looks like par excellence, an effective theory of something. I won't say what.
Like comparison.
But I mean, probably I would say string theory because that's where I hang out. But just trying to be starting from the low energy point of view, it's useful to try to think about what are the defects of gravity from this analogous point of view, which is part of another general line of thought that I've been attracted to, although I don't have any result. But it's also, of course, another famous effective theory, of course, is just chiral symmetry in nuclear physics, right? People in reactors don't want to hear about quarks. They just don't want to hear about quarks or gluons or anything like that. And yet, they're down there. And we understand quite a lot between the links between the non-renormalizable pion theory, which you work at. And you can see clues hiding in the pion theory that tell you about what's happening downstairs. So similarly in gravity, we should be searching for these links, both if you have your sort of parallel plate defects that you see in the Heisenberg style, or also are there hints that you can see elsewhere. I think these are productive lines of thought. I don't have anything to propose other than I have my favorite way of thinking about how you got the effective field theory, which is integrating all the string nodes. But it's useful to try to phrase this just purely in terms of what's wrong with gravity, Professor Einstein.
One thing to start with is exactly causality. I mean, you have time machine in the if you don't start adding, quantum field theory and try to enforce a chronology protector.
You mean like in the back side of the Kerr solution?
You can have, well, not just inside the Kerr solution. You have plenty. You have, rotating strings, von Stockholm space-time, Gödel universe. Gödel universe is Gödel invented the universe exactly because he was speaking with Einstein, and he gave it as a gift for a birthday of Einstein. There was a special issue, and invented this universe which has the same energy matter content of Einstein's static universe, nonetheless has closed-time-like curves everywhere. Everywhere. It's a nightmare. In fact, Einstein was not amused, apparently. But because Einstein insisted that yes, times is relative, but there is a sense of time for each one of us. And then the other was saying, no, you have to give up time because I can build solution where time doesn't have a true meaning. And that is the universe. And warp drives, wormholes can be used to do closed-time-like curves. So to me, that is another interesting branch because it's really a breakdown of the theory that is telling you that the theory is not fundamental. And I'm afraid effective field theory of gravity are not going to solve this kind of issue because these are related, are structured into the causality. You need to have a theory that proves that all the space-time are always globally hyperbolic. But that, how you can do it, because it's a kind of topological statement. You see what I mean?
Okay, thank you. I've seen that Astrid wanted to say something, so please, Astrid.
Yeah, I wanted actually to pick up on something that Kelly was saying, and that leads to this question of what actually happens when the EFT breaks down. Because the examples that Kelly was mentioning, or we've been discussing, like Euler Heisenberg and chiral perturbation theory, when these EFTs break down, there are new degrees of freedom. And Kelly was suggesting, well, when the EFT of gravity breaks down, then there's string theory, which is new degrees of freedom. Right, but there's also a much more conservative possibility, of course, right, that the EFT breaks down because we've not accounted for non-trivial structures in the renormalization group flow, instead of not having accounted for new or more microscopic degrees of freedom. Right, and in this way, you can, of course, in principle, UV complete an effective field theory without ever actually having to change the degrees of freedom. And I feel that when we are talking about the breakdown of the EFT for gravity, we are much too quick to jump to this conclusion that this implies that there must be new and probably non-quantum field theoretic degrees of freedom that we are missing. And there is an alternative possibility, which is that we are just missing non-trivial structures in the renormalization group flow that lead to things like asymptotic safety and allow us to UV complete without having to change the degrees of freedom, just having to account for the ways that the different interaction terms interplay with one another. And that, of course, also then presents a whole different aspect to all of the phenomenological questions we would ask about the breakdown of the CFT, right? Because non-trivial renormalization group structures manifest themselves in very different ways than new degrees of freedom that would show up at the scale, right? We would not have the analog of pair creation that we have when the electron and positron shows up in beyond Euler Heisenberg. We would have other phenomenological effects.
Mm-hmm. Yeah, this is this other possibility of asymptotic safety. Yeah, like I was also mentioning before, because you have this infinite number of terms, but it's possible that maybe because of renormalization group effects, there is some critical surface with a finite number of parameters. Yeah, this is also possible.
Can I just interject about asymptotic safety? I mean, I like to try to be friends with the asymptotic safety.
Not to be a friend?
Yeah, in the sense that it's useful if there's a kind, again, kind of a meso-effective theory, which would be the asymptotic safe point of view, leaving off until the ultimate tomorrow, what's really happening, whatever. But there are some things that, for example, I gave this example, that the paper that we wrote with Jean-Luc Lehners, starting with the curvature squared gravity, which changes together with this assumption that the action should, starting from the, as Dua Lipa says, way back, right, the very beginning, until now, should not diverge. Okay, the Euclidean action should not diverge. In ordinary Einstein theory, you don't get any restriction from that, but in quadratic gravity, you do, and you learn the Penrose-Weil curvature hypothesis, at least in the family of the Bianchi-9 universes, right? And that was a specific little exercise in the context of the curvature squared theory. How much does that generalize to the more general family of asymptotically safe theories? I don't know, but it's a question that want to ask itself. And I think it was one of your questions on your first slide about initial conditions.
Yeah.
Can you learn something about
Yeah.
cosmology?
Was my last question. Yes. Can we understand the mechanism that selects the initial conditions for inflation and effective theory of gravity? Right? Yes, this is a good point. Thank you. So, other questions in the audience? Please.
Yeah, maybe coming back to the discussion about natural and unnatural, standard and non-standard EFTs. So I'm wondering if, I mean, I can believe that there are unique completions that in the low energy predict a hierarchy of EFT scales, which appears unexpected. But would you say there is still merit to the idea of having a natural EFT, or should we just entirely throw that concept out?
Astrid, please.
I would say the natural EFT is the simplest one, right? Because you basically know the size of all coefficients. You have one free parameter, which is the cutoff scale, and then you say all of the other coefficients are order 1. So it's definitely the simplest possibility to explore. But when you're finding that EFT is insufficient to describe some situations, or it's maybe constrained experimentally, then that doesn't mean that an EFT description of the setup has broken down. It just means that this naturalness assumption has broken down, and then you should open yourself to having EFTs in which you need to really account for more of the free parameters and account for the possibility of having some of them arbitrarily very large, right? So it's a good starting point, I would say. But when a natural or a standard EFT breaks down, it doesn't mean that an EFT description of the physical situation that you're considering is breaking down. And I think that this is where often this possibility is missed in arguments.
Thanks.
Yeah, I mean, you already know that, for example, the value of the cosmological constant is not natural. This is the essence of the cosmological constant problem.
Yeah, exactly. That was something.
Yeah. Yes.
Lavinia,
please.
Yes, I just wanted to add, sometimes if you just go with the standard effective field theories, which are, of course, simpler because you don't have this hierarchy or very complicated rearrangement of the operators, then you also very often run into the unnaturalness problem, right? That as soon as you consider loop corrections, you see that your classical standard EFT operators become very, very large contributions. And sometimes when you allow for, let's say, less simple, non-standard effective field theories, the operators are arranged in a very, very specific way, but they help actually with your naturalness problem, such that if you now go and compute your loop corrections, you see that their contribution to your classical non-standard EFT are not large, and these coefficients are actually natural. So there is, I guess, not only in terms of the way how new physics enter is a benefit, but also in terms of how this new physics is stable under quantum corrections. There's also this benefit.
Yeah, I had a question for Stefan. So there is this program in amplitude community where people apply the specificity and authenticity bounds, and they infer what the unique completion should be. So you think for quantum gravity that wouldn't really work?
It depends what problem you want to address. If you want to address a problem like singularities and time machine, GR, and so on, for the reasoning I was saying before, I'm skeptical that could solve that. But it doesn't imply that, you see, there could be several layers. There is GR, there might be a UV complete quantum field theory, but that doesn't imply that there isn't another layer. And if this UV complete quantum field theory is not predictive anyway when you get a singularity, then it means that it's incomplete. It means that you need another layer. And to me, the other layer would be what we would call non-perturbative quantum gravity. That means the theory where somehow you have fundamental discreteness and quantumness, and you have to emerge a continuous and classical space-time. But by the way, the continuous limit and the classical limit do not commute. They're not the same. and the order in which you do them might be very relevant to your phenomenology. So I'm just saying that there could be several layers of description, and even if it is successful, a program where you have an asymptotically safe quantum field theory, doesn't imply that it has to solve everything. It may be very good, again, for computing scattering amplitude, for other things. You see, theories are good for depending on the question you ask. There are very good questions that can be answered very well in Newtonian gravity, and nobody will use GR to answer them.
This question reminds me of another aspect which has not been discussed here. Going back to Niedermeyer. Going back to Niedermeyer's approach to asymptotic safety. One of the points of his paper was, well, of course, there's a correction about the asymptotic freedom of the R-squared term, which Roberto Percacci and Donahue and company have now readdressed and say, don't worry about it. That can also be asymptotically free. So let's take both the Weil squared and the R squared as being authorized to be asymptotically free. But Niedermeyer in his paper then went on to say, so you have those two coefficients, the ones that you put downstairs are going to zero, by the way, so you know where they are. That means that those coefficients are getting huge. So the naturalness is that both of them are blowing up, right? But, and then you may worry about the ghost, but Niedermeyer also said there exist trajectories. Now you have to choose which one to go along as you head in towards the non-Gaussian fixed point in the two remaining coefficients, the cosmological constant and Newton's constant. There exist trajectories along which the Hessian, the matrix of second derivatives, this is in Euclidean treasury, has no zero eigenvalues, and so you don't hit the ghost. It's out there, but you miss it. So that, I don't think anybody's discussed here during this meeting. That's another point of view, that there could be dangers in the woods, but you just be careful not to go too close to the bear. And maybe that has something else to do with these, on those trajectories. Now, can you have other things work out with the right ratios and so forth that you want? And I don't know anything about that. But within the context of asymptotic safety, that's a question you can ask. There could have been a ghost, but you don't hit it.
Yeah, I think that this is a possibility that's been discussed in the literature.
Yeah, that was definitely actually the main point of Niedermeyer's paper.
Others,
From Salvio.
yeah. It's a possibility, yeah. See, maybe Lavinia wanted to ask something, or maybe misunderstood.
No, I just wanted to say about I think what Stefano was saying about basically these conditions that come from the UV. So I mean, imagine you have a specific operator of your non-standard effective field theory, which allows very specific background field configurations where you have these closed time-like curves. But now, if you further put constraints coming from UV, like positivity or unitarity or asymptotic safety, then you could basically translate these constraints in a way that maybe this operator is not allowed anymore, or its effect will not allow anymore to build such closed time-like curves. In a sense that even though you have a complete ignorance about what your UV theory was, by assuming certain properties of whatever this UV theory is, can restrict your non-standard EFT in a way that these naively unphysical field configurations are then removed.
I don't think, Lavinia, that is enough to forbid some of the operator. It's really the plasticity of space-time that allows these closed time-like curves. You can always use rotation to generate closed time-like curves. So it's really that you have to put a constraint on your theory that will spit out only globally parabolic space-time. And that is very difficult to see how it can be generated by adding operators to Einstein. You see what I mean? It's really that you need something that selects for you a structure of the solution. And for example, was the hope for Hawking in 2004 when he was saying that he may have solved the information loss paradox. He was basically at the end trying to argue that in a path integral, when you have a black hole, you don't have a contribution in Euclidean and quantum gravity. You don't have contribution from non-trivial topologies, which was like to say that your space-time, the dominant part in the path integral was coming from global hyperbolic space-time. And then if you hyperbolic, you don't have the evaporation diagram that creates the problem with information loss. You have a regular black hole of some sort. So I'm just making an example. There you could, but you have to recur to Euclidean quantum gravity. You have to go out of the standard paradigm of a field theory. You see what I mean? And adding operators is difficult to imagine how you can add that. It's not so much that a single operator can screw up things. They already screw up. You want to add operator that cures things. But how an operator is going to forbid solutions which are not globally hyperbolic? It's very difficult to see, no? Because
but I mean, in practice, I guess what you do is you look at very concrete solutions, right? You have certain background field configurations, and on top of that, you look at some perturbations, and you try to see, can they actually propagate this information on this very specific background field configurations that I just constructed, and then depending on whether or not this solution is natural, then this perturbation will actually propagate and your effective field theory will not break down. But what I was saying is maybe you have these very non-trivial operators such that this background field configuration will never be of such sort that your perturbation will be stable. Basically, you will never be able to propagate information on such background. So then there is not really a point about talking about closed time-like curves. Because there is no information that can propagate without breaking your EFT, so to say.
You need to really forbid Cauchy horizon to form anywhere in your space-times.
Yeah, I wanted to add, echo that. It's one of the things that Gary Gibbons likes to emphasize to me, that these Cauchy horizons are also singularities. Because if you have the quiet solution like Kerr, and as soon as you bring a drum in there and you perturb the space-time, you're going to have a singularity developing on these Cauchy horizons. So your proposal, but so is it, first of all, the case that these closed time-like curves always occur behind Cauchy horizons? It happens, yes. I guess, in the Kerr solution. Yes. I know where to find it in that other.
Always, because a chronological horizon, if you have a sane space-time and you have a region instead where you have closed time-like curves, then there must be a chronological horizon. A chronological horizon is just a particular kind of Cauchy horizon. And so there are always Cauchy horizon. The alternative is that you have space-time which is totally sick, where there are closed time-like curves everywhere. And basically that is good. Gödel you have everywhere. It passes through a closed time-like curves because it's homogeneous. So if you see a closed time-like curves here, I can live here and see a closed time-like curve there. So, but yes, there are always chronological horizon if you have a sane region and a region with closed time-like curves. And in fact, the Cauchy horizon of Kerr, the closed time-like curves in Kerr are close to the ring singularity, which is behind the Cauchy horizon. But Kerr, you can say, okay, I mean, that is the point you make is very important, because Kerr, as we know it, the Kerr that we say, the black hole that we see in the sky are Kerr black hole, it cannot be true. We cannot, cannot be exactly the Kerr geometry, because the Kerr geometry, the interior is unstable. And now the standard law is that you cannot see this, outside of the outer horizon, this instability. But if the Kerr geometry is the only vacuum axisymmetric solution of general relativity, and if is not the Kerr solution, the one that you really have realized because of the stability of the inner horizon, it cannot be vacuum. And then it cannot be exactly Kerr, it can be very close to Kerr. And for an extremal black hole, this Cauchy horizon is just behind the outer horizon. It's not far away in the core.
Exactly.
So for a near extremal black hole at 0.9 for the spin factor is dangerous. So we have to accept that the black hole in the sky, they cannot be exactly the Kerr geometry. Or you have to find a way to cure this instability.
Yeah, but you were complaining that how do we see this like by adding operator? But that's exactly the point. I mean, in quantum gravity, you will have a modified dynamics compared to general relativity, and then it is from there that this type of solutions come from that hopefully have no Cauchy horizon and that.
No, but I mean, I was referring to the point of having closed time-like curves. So the Cauchy horizon, it may be possible that you have a solution that, in the case of the black hole, is regularized. It's simply by adding extra operator. But the problem is that it's very difficult to see. Normally, if you have a higher curvature operator, it's very difficult to see how that could give you the kind of avoidance, generic avoidance of any kind of singularity. It may happen, and it may not, but this.
I mean, Astrid might comment on that.
She already has her hand raised.
Yeah, I just wanted to say I'm aware of one way in which one can address this question of how to remove a sort of spacetimes with certain non-local properties, right? Like, I mean, closed time-like curves are non-local, horizons are non-local. How one can remove them from a theory. And it is definitely not within standard EFT. But what you can do if you want to remove, for instance, a black hole horizon or configurations which have black hole horizons from the path integral, you can use horizon detecting curvature invariance in your action, but you actually have to use their inverse. Then the action diverges whenever you have a horizon, and this leads to destructive interference in the Lorentzian path integral. And so you get rid of any configuration that has a horizon. Potentially, you might be able to do something similar with closed time-like curves, but because you're targeting a non-local property of your spacetime, in this case the horizon, the action that you have to use for that is quite non-local, and so it's definitely not an action that we would. I mean, it's not an operator that we would include in the standard local EFT expansion, and it's not even clear whether this is a sensible dynamics at all, or whether it immediately leads to much worse problems when you include these non-localities. But I tend to agree with Stefano that I find it difficult to see how you write local operators that get rid of something like closed time-like curves.
Exactly, but if you start to see that you have a working theory with non-local operator, then for me is a smoking gun of a non-perturbative quantum gravity. Because in a sense, if you want to have Lorentz invariance emerging from quantum and discreteness, remember one discussion with Raphael Sorkin, he would say that for him there must be some kind of theorem somewhere that tells you that if you want to have the emergence of space-time with Lorentz invariant, then you need to pay the price of some sort of non-locality. Non-locality for me non-local, so that for me is anyway departing from standard quantum field theory, as you say, non-local term. If you have a non-locality and you find non-local terms, for me that is a smoking gun, then there is a more deeper layer underneath with a different notion of causality. Because there isn't a space-time, there is a kind of just the correlators between fundamental objects there that are relevant. And they do not need to satisfy any Lycon because the space-time is not there at that level.
I just wanted to remind people back in the 1980s or maybe 1970s, there was a movie called Back to the Future, which involved, this is now an extinct type of car with DeLorean, had gull-wing doors. So we could call these spacetimes you're trying to banish DeLorean spacetimes.
Yes, exactly.
No, but just to add to what you said, you don't need to go distinct to have non-locality. In principle, you could have a quantum field theory of gravity, which is ultraviolet complete and non-local at high energy.
Yeah, because by loops, how you generate the non-local operators?
No, that anyway, like you must have like in the IR at least logs, so by you must have non-locality in the IR in the effective action. But in principle, in a quantum field theory of gravity that is ultraviolet complete is pretty. It's likely that the ultraviolet completion will be non-local.
No, but that I'm not saying, I didn't say anything against that, but I'm saying if the ultraviolet completion is non-local, then to me is more a smoking gun that there is another layer.
Right.
Because or you give me a fundamental reason why you have to introduce non-locality, and what is determining the scale of non-locality. Well, it's very natural. If you have, I mean, there are examples already, no, in the propagator, the box propagator in causal set becomes an f of box. It's a non-local operator. I mean, it's a toy model, but still it shows you very clearly, no, that you need, you pop up this non-locality at the, exactly because you're enforcing at the fundamental level, even causality condition with Lorentz invariance, if you like. So I'm just saying that, of course, we can discuss forever because I mean we don't know everything that can happen. I'm just saying, and we are telling us our gut feeling here because we don't have it. I think nobody of us has a proof. To me, it's much more easy that if you tell me the UV completion theory needs to have this non-local term in order to work, then to me it is even a more, I would say, well, these probably are coming from the fact that there is an underlying layer from which this spacetime emerges with its own geometrodynamics, which has this non-locality where the scale of non-locality is related to some property of the underlying layer, because this is what I've seen in many examples, at least two, causal set and group field theory.
I mean, it could be, but could also not be.
But if it's not, then you have to tell me where this is coming from, because these are fundamental. You are postulating that they're not generated by loop. Of course, we can generate also by loop.
No, but I mean, we need at least one scale, right, to define stuff. So I mean, unless you live in a scale-free universe, at some point you need to
but the fact that the scale determines non-locality is not trivial, because the scale can determine many other things. It can give you a frame, it can give you. So I'm saying that if you select non-locality, you are saying, I mean, that is an important information. I wouldn't be content to just say, okay, it is as it is, and this is God given. It's clearly telling you that there is something deeper underneath, to me. You have to explain where this non-locality at the fundamental level is coming. And it's very easy to imagine, to see it emerging if you assume that you go for discreteness, for a discrete, for the fact that the spacetime is emergent. Emergent in a very broad sense. I'm not saying specifically one emergent. Still, you can have gravity on the theory. I'm not advocating any classical point of view for spacetime. Simply, if you see this non-locality, we have seen it emerging from the discrete version of spacetime.
Astrid.
I just wanted to follow up on Stefano's comment about the non-locality in causal sets and say it's actually a nice example where if you just take the quantum field theory that you have this non-local D'Alembert that you can derive from causal sets, but if you forget about its derivation and treat this as a quantum field theory, and then you ask, well, what happens to a scalar field that has this type of propagator, you see that it develops a Landau pole at the non-locality scale. And so the QFT breaks down as soon as you reach the non-locality scale. And then the answer is, well, therefore there has to be this discreteness scale that you originally had in causal sets has to equal to the non-locality scale. But it's sort of a nice example where if you really consider the physical consequences of the non-locality in a standard QFT, you see that the standard QFT breaks down because it has a Landau pole. It tells you it needs new degrees of freedom. And by the way, just as an aside, you see that once you add matter and you stop thinking about just gravity on its own. But that's maybe a whole different discussion topic of whether or not to include matter and whether it matters.
You want to say
I wanted to something still bothering me about Robert's discussion about the two regions not having anything to do with them. In Starobinsky inflation, he doesn't actually put a scalar in there. It's just R squared, right? Which is a nice, generally covariant term. We normalize it, it's asymptotically free, should be big, etc., which is what he wants, right? So it's actually not a scalar, it's R squared. And then there's Weil squared as well, but maybe we ignore that for the first 2 minutes, right? It's actually a completely well-posed renormalization problem. There's a good reason why that coefficient is humongous.
But there is
can you rephrase your complaints in this language where you say
you
have nothing to do with one another?
What you're saying is that this is safe. But when we go on and include perturbations, then what we do is we look at linearized fluctuations around the background, we treat them as effective fields. We expand them in Fourier modes. And what I'm saying is that Fourier modes that violate this are just sick. So this is this problem. Stravinsky inflation is not immune from this problem.
Well, I'm happy to take the r plus r squared part of r plus y squared plus r squared and allow you to shake it, to consider the fluctuations by all means.
But if you have wavelengths which are smaller than the Planck lengths, you are in the zone of ignorance of an effective field theory. Because you in order to avoid the Planck catastrophe, you need an ultraviolet cutoff at a fixed physical length scale.
But Kelly,
Well, if we normalize the thing.
You're talking about Stravinsky inflation as an effective field theory, or quadratic gravity as a Gubitosi?
I'm a renormalizer, right? I start out, you give me a problematic theory, so I renormalize it. Okay, so now I've dealt with that.
But the renormalization is throwing away the contribution of modes with wavelengths smaller than the Planck.
Sorry, say again?
Renormalization is throwing away the contribution of wavelengths of modes with wavelengths smaller.
Normalization is just handling the problem of the infinity, subtracting it from the theory, and then you have a residuum which you then have to live with. Right.
That's what it is. What I said. A mathematician would say you are just throwing away the contribution of these modes.
Oh, I mean, yeah, there have been complaints about renormalization since the 1920s, but no, that requires some alcohol to discuss. In an ultimate finite, this is where I try to be friends with my asymptotically safe people, which hopefully eventually comes a totally finite theory, which at such tiny distances that all sorts of other things are happening. But let's not talk about those this afternoon.
Let me try an argument on
That's the argument for just doing renormalization.
Let me try an argument which says that in the presence of gravity, you cannot do that. Okay, and this argument is the following. Instead of working perturbations forwards, let's work perturbations backwards. There's a measure zero set of fluctuations, if you work backwards, that at this point give you vacuum. So if you don't have vacuum, you have a black hole. Effective field theory breaks down. So that's my reply, by the way, to Cliff Burgess.
Oh, yeah.
So there are very few people who in press have actually been arguing against the TCC. There are two papers, one of them by Cliff Burgess and collaborators, and this is my reply to him. He's neglecting this. He's neglecting the fact that the problem comes from the exponential expansion of space. And then the other person who criticized the TCC is Dvali, this paper by Dvali, Tehagas, and Ryota. And if we had a Zoom talk, actually, he completely agrees that you need to go beyond usual effective field theory.
You said
he just doesn't like the words that we're using.
Sorry, Robert, you said that Burgess had a paper on this?
Yeah.
Okay.
Burgess has a paper. It's Burgess, Quevedo, and someone who is originally Sri Lankan, whose teachers at University of De Alves.
Yeah. Santa De Alves.
Yeah. So it's Burgess, Quevedo, and De Alves.
Wanted to say something?
Maybe, yeah, I mean, I can tell you, I can comment now about what I told you like a couple of hours ago. There is a way out also to this argument that one goes beyond the effective field theory, but still remaining within the framework of quantum field theory. And what you need is either a strongly coupled regime or non-locality, and then you avoid the problems with unitarity that you were talking about.
Yeah, I agree.
And then it's fine. I mean, it's just that you need a prescription to determine your EFT coefficients below the scale at which the EFT breaks down. And those coefficients can be large, in principle.
But you need to do the calculations
Yes, yeah,
in the
absolutely.
context of your strong hypothesis.
Yeah, absolutely.
I completely agree.
And since if there is no comment, I also want to comment on something that you mentioned at the beginning, saying, oh, well, maybe EFT is too restrictive because it assumes that there are no additional degrees of freedom. This is the standard point of view of effective field theory, that you just think as, well, there is the graviton and nothing else, and then I build my EFT expansion like that. But if you would like to, I mean, if you want to study a theory that also has the scalaron and the ghost, I mean, you can generalize the concept and say, I want an effective field theory that has these degrees of freedom, and they simply are two different universality classes of effective field theory, and you can describe even them together. So it is still fine.
You have said this before. You can do some more general effective field theory where you have more degrees of freedom. But insist that I don't see quadratic gravity as an effective field theory. And by definition,
no, but it depends on what you mean, in the sense that there are, of course.
In my meaning, I don't mean this. Then it's another meaning. If you treat those coefficients C2 and C2 prime in front of R squared and Y squared term as a perturbation, then this is an effective field theory. In the sense that you are not including those coefficients, for example, in the propagator of the metric, while you treat it perturbatively.
No, but you should start with an effective field theory that includes these degrees of freedom to then do the matching, right? And then the point of view of quadratic gravity, which is in principle a UV complete, it is a UV complete quantum field theory, is that you compute the coefficients of your low energy effective field theory. And then you can match it. I mean, the effective field theory doesn't need to know about your ultraviolet radiation. It is all the whole point.
Scale of the extra degrees of freedom, you can construct an effective field theory that takes into account these extra degrees of freedom, but it's valid at energy below this extra degrees.
I mean, you just below the scale of inflation, you just write down your infinite power of terms, and then you come with your quadratic gravity, and you say all of this is zero, and these three coefficients are 1, 2, 3. So it's fine.
Another thing, maybe it's good to clarify, is that I think is most probably you cannot cure any of these pathologies, singularity, whatever, with an effective field theory approach in the way I defined before, because of course, if the coefficients are treated perturbatively, you will have a small modification. If you have an infinity, you cannot get rid of it with the perturbative parameter. But this was exactly the point. So I don't think that one can hope to solve the problems of general relativity within an effective field theory approach. It's just that I think it's interesting to go and look at places where the breaking of effective field theory occurs, so that one can maybe have signals of UV complete quantum field theory or string theory or whatever complete effective field theory. Yes.
Okay, so in the context of what you just said, I have a question for Astrid. So in the asymptotic safety program, does one get black holes with singularities? As if we don't know.
Yeah, the answer is we don't know. You can construct sort of toy models of black holes inspired by asymptotic safety, where you're basically upgrading a classical metric and account for the running of the couplings, and then you generically get a weakened singularity or no curvature singularity. But I mean, this is not deriving the full effect of action and looking for the solutions. This is starting with the classical metric and then upgrading it by some of the effects that we think are the dominant ones in asymptotic safety. So the answer is we don't know yet. But I would assume that this has to be the case, basically because of the physically what asymptotic safety is scale symmetry above a certain sort of minimal measurable scale. And so I think what that implies is that that is the minimal curvature radius that you can have. And this gives you a cutoff on any curvature invariant. But I mean, that is, of course, a hand-waving argument, right? And yeah, still requires more work to give you a proper answer.
There's a somewhat connected, really nice work by Bob Oldham, 20 years older, so 15 years. He looked at local theories with higher derivative terms and looked at generalizations of Schwarzschild in these theories. And what he showed is that generically, once you're at 6th derivative order, you do not have a singularity at the origin anymore. And since in asymptotic safety, we have all these terms, it seems like kind of natural that we fall into this reasoning, at least from my perspective.
So a follow-up question.
Yep.
The Penrose diagram for these solutions, does it look like the Penrose diagram of Minkowski with some modifications at the origin?
That I really don't know. I mean, the paper really just studies, okay, you have spherical symmetry, you throw that into your equations of motion, and you expand about r equals 0, and you see that you cannot have singularities there. That's the kind of idea. And I think it's also kind of intuitively, or you can make an intuitive argument because the trace of the equation of motion has now r plus, I don't know, y cubed or something like that is 0. So you do not have that Ritchie-flat matrix of solutions anymore, but different curvature invariants are linked, and then...
So they're not vacuum solution. So do you have black hole maybe that...
It's not GR vacuum solutions. Starting at the two-loop counter term y cube, all the solutions that you have in GR are not exact solutions anymore. But this is what we expect, right? You do not expect that generically solutions of GR are exact solutions of quantum gravity.
But the answer to this question, I think, is straightforward, that there must be at that point some regular strong gravity region in a Helfer-Minkowski. Because if you don't have a singularity, you will not cut your space-time. So you will basically just have a strong gravity region, or with or without horizon. I don't know what is your solution.
Yeah, sure. I'm just saying that the paper doesn't go that far. It's just saying that you look at where the problem is in GR, and you see this problem seems to be resolved. That's the statement.
And there is also an alternative way of understanding this. So if you, I mean, Astrid can comment on that better than me, since she has a previous paper on that. I mean, if you think about the mechanism of singularity resolution via the suppression of singular spacetimes using the gravitational path integral, one can see, and this has been done recently by Joanna Borisova, who is a student at Perimeter, that if you have an action with infinitely many derivatives, then you can manage to suppress all singular spacetimes close to or equal to 0 that you can come up with. So, but it's really, and I mean, this would be compatible in a sense with the statement in asymptotic safety. I mean, if you have an asymptotically safe fixed point, your Bayer action most likely will have all of these infinitely many higher derivative contributions.
Yes, Lavinia.
I guess one problem which usually always occurs, it doesn't matter where, like if you try to do non-local or any type of other different operators for which you got this non-singular new solutions, or maybe you used a theory which is not general relativity but explicitly modifies it, then you can actually construct solutions where you don't have black hole singularities or cosmological singularities. But usually the problem comes always as soon as you consider perturbations, small perturbations on top of such interesting looking solutions, then you see always that they explode at your face, that they are not stable. And so one could then argue that maybe there are some non-perturbative effects that you need to take into account. But then this would also mean that your naive classical field configuration that you considered in order to construct this solution was not correct to begin with. So actually, this is not a physical solution. So in this sense, I guess it's, at least from a theoretical point of view, it's not very difficult to get these solutions. The problem is always that they are not stable.
Please.
Yeah, so I agree completely that the criterion for singularity resolution is not just finding a solution, a homogeneous anisotropic solution without a singularity, but the perturbations have to be well behaved. So I completely agree with you, Lavinia.
Okay. Other questions to the panelists?
That point is very much related to the Cauchy horizon question too.
Well, then if there are no other questions, I would say we finish this panel discussion. And thank you very much to the panelists.